Great. Welcome to episode 5, I think, of Statistically Speaking. Today we're covering the topic that everyone seems to use. When you ask people what do they use in biostatistics, very, very frequently the answer that comes back is t-test. Now, t-test is not all things to all people, but you would think so based on the kinds of analyses we see. So today we're going to talk about t-test and its cousin, the u-test, and evaluate some of the things that need to be true for that to work out well. Okay? So we're going to discuss difference tests. So we will talk a little bit about statistical history in the context of beer production and in the context of bullet production. So I understand that this is a wine-growing region, but some people here do like beer, correct? Mm-hmm. Great, okay, good, yes. And some people, in fact, like dark beer?
Probably good.
Okay, all right, good. All right, I thought for years I hated beer, and then I had a stout, and I was like, this is actually pretty good. So today, we will investigate some of the statistics in beer production. Excellent. And then from there, we will talk about test statistics and p-value production. A bare minimum of talk about eugenics today, really. I mean, that's such a negative part of our history. I don't want to spend every week talking about that stuff. So instead, beer and bullets. All right, and then from there, examples of difference testing as implemented in R. Okay, so let us move ahead to the next slide. So we start with William S. Gossett. When you hear the name student, the pen name student, you should think William Gossett. William Gossett is one of those folks in statistics that I think all of us can respect a little bit. He found that his degree in chemistry from Oxford University, I got that straight, right? Yes. Was a pretty good entree into industry. He thought to himself, I'll go work in industry with all this chemical knowledge that I've acquired in my Oxford education. And off he went to the Guinness Brewery. Now, I've heard wine people say that beer people always want to make their batches exactly the same way, whereas for the wine community, having a slightly different terroir or whatever each month, each year of production is considered valuable. So maybe that makes beer production boring, but in fact, it became one of the grounds on which our statistical theory about reproducible manufacturing were created. And William Gossett stands behind an awful lot of that. So back in 1904, he began working for the beer company. He convinced the people at Guinness that it would really help his work at the company if he would take a quick leave of absence and spend a couple years working with this person called Carl Pearson. I think we all remember Carl from a couple weeks ago. Argued that child labor laws were stealing money from the public. All right, so he decided that this Carl Pearson would be an interesting person to work with and started learning a bit more about statistics as part of that. Now, in 1908, he published through Carl Pearson's journal, Biometrica, a paper describing something called the t-distribution. And that publication of the t-distribution was the start to students' t-test, because he had to publish under the name student. He was not allowed to publish under his own name because the company for which he worked, Guinness, did not want it to be known that they were hiring a statistician. Not because they were ashamed, but because they thought this gave them an advantage. So this means that if you, as a scientifically literate person, leave this university with a master's degree or a PhD degree, you may not go into academia. You might go work for industry. And what you know about dealing with numbers may be your entry point for them. So I hope that these lectures on statistics help inform your mind about that and make you feel more comfortable in this realm, so that when you do job interviews you can say, oh yeah, I love statistics. I love that stuff. That's awesome. All right, so on we go. So Guinness wanted to protect their commercial advantage in having hired Gossett, so they just forced him to publish his papers as student rather than as Gossett. Now, what is there to respect about Dr. Gossett? Now, he became very prominent in the British statistical fraternity, even though he worked for Guinness for essentially his entire career. So he was actively engaging with academic researchers in this space, and frequently he was the person who was kind of cooling off the arguments between Pearson and Fisher, or all these different names that we're going to be talking about over time. So in a lot of ways, the caricature of scientist is of somebody who's highly opinionated and who doesn't play well with others, right? I mean, do we really admire scientists for their social skills? Not so much. Not so much. But Gossett was one of those people who could help people who hated each other to have a constructive conversation. And so, in the British fraternity of statisticians, he was actually a very important figure for helping to modulate these conversations. So I think that is very much worth respecting. There's a very good blog post here on Priceonomics about his extended career in this space. Okay, now I want to tell you another story, this one about Frank Wilcoxon. Now, Frank Wilcoxon has a really interesting young life. He was born in Ireland, and from that you might deduce he's Irish. But in fact, he was from an extraordinarily wealthy American family that had rented out an Irish castle for the mom to give birth. Freakish and weird, right? Now, his twin sister died immediately upon birth, but he himself was healthy. Now, you might think that being, pompously wealthy and American means that he would be able to just sort of coast by on his laurels. But in fact, he was a little dissatisfied with some aspects of growing up. When he was 16, he ran away from home, right? Running away from millionaire parents, the pampered life, etc. He ran away and signed on to be a ship worker, right? So he signed on to be a sailor on the ship. He spent 2 weeks chipping paint off the hull. And after that, he said, "I'm done with this," and ran before the ship sailed. So he believed that he was on the run, that either his parents were after him to retaliate for his having turned his back on them, or maybe the ship company was after him for having broken his contract, right? So he hid in the wilds of West Virginia. Not so wild, but there you go. And it was only much, much later that he decided that he would try to reconcile with his family. And they welcomed him back and repaid that trust by sending him to military school. So, so there you go. He graduated from military school. I believe he went to Rutgers for his undergraduate education. And then he did a PhD in physical chemistry at Cornell. So I would submit that he had access to great resources through his family. He had a great mind that couldn't really hold itself to ordinary pursuits. And then he challenged himself after returning to his family to take on these things. And then he graduated with his PhD. Do you know how old he was at the time he finished his PhD? He was 32 years old. And that was considered old. He was old, right? So what academic career could he actually have, having started his career late at 32? I got my PhD at 30. I was really slow in grad school too, I'd have to say. So here he was. He's finished a physical chemistry degree. What does he do? He goes to work with in the space of chemistry. And with the outbreak of World War II, he found himself thinking, well, I know some things that could be very useful to making the manufacture of bullets and ordnance in general safer. Right? So he's already got some statistical framework in his mind that the lessons we know for reproducibility and for reducing variance and so on, that these are skills that are applicable to industrial production. So he convinced the Army office that he should be involved in this ordnance factory, and for years later, decades later, he was still talking about the fact that he had a 0 accident rate during the time that he was in charge of this ordnance office. So that's a pretty good thing, right? Now, I want to note that although he'd gotten his degree in his PhD in physical chemistry back in 1924, his attention had already drifted just 2 decades later. A mere 2 decades, right? So he had begun thinking about statistics as a discipline where he wanted to work. And he started publishing papers in this space in 1945. The second paper he published introduced this approach to what we call nonparametric statistics. Okay, so when we talk about the t-test, we're describing a parametric test intended to deal with whether the samples from two cohorts are different or not. But there are certain expectations that t-test has about the data. So the presence of outliers or a non-normality to the variance. these are really bad things when you're trying to use a t-test. So when you think Wilcoxon, think about a non-parametric pair to t-test. All right, so there's the t-test, and then there's what we sometimes call a w-test or a u-test. So we'll be talking about u-test versus t-test quite a lot in the course of today's talk. Okay, on we go. Oh, also, he was kind of renowned for riding bicycles to work throughout his career, and as his career progressed, he eventually had to shift to a motorcycle. Thus the picture of him on the motorcycle, which I borrowed from this URL at the bottom. Okay. I know it's before lunch, and this is my last chance to talk math with anyone today, so we're going to talk a little bit about math. When we use a t-test, when we use a u-test, the non-parametric side of this, we generally use these tests to compute a t statistic or a u statistic on the basis of the data we've got. And that t statistic or u statistic then gets translated into a p-value. All right? So you've got your data points, you summarize those data in a test statistic. The test statistic can then be looked up in a distribution to determine a p-value. All right? So step 1 is data, step 2 is the summary of the t statistic or u statistic, and then the third step is looking that up as a p-value. So when we compute these statistics in the student's t-test, I think we might remember seeing those bar notations used in a previous slide. Everyone remember the bar? Okay, so the bar represents the mean. So in the student's t-test, in the numerator, the top of the fraction, we're comparing the mean for cohort 1 and the mean for cohort 2. So if those numbers are very far apart, that gives us a large number. If they're very similar together, we get a very small number there. And on the bottom, we have something called the pooled standard deviation, which is effectively sort of like a geometric mean of the standard deviation of cohort 1 and the standard deviation of cohort 2. So it's, you can look up the math if you really want to. I'm not going to focus on it tremendously here. And then we have times the square root of 2 divided by n. So the number of samples that you've got is going to figure into the value of the t statistic. So I've tried to give a little translation of those over at the left as well. Now that's different than the way we compute a U statistic for this non-parametric test. So when we use, I've shown you a whole lot about Frank Wilcoxon because his life is really interesting. Two other people who worked in this area who kind of built on his work are called Mann and Whitney. So we frequently refer to this test as the Mann-Whitney test. You'll see some people call it the Wilcoxon. You'll even see the Mann-Whitney-Wilcoxon test or the Wilcoxon-Mann-Whitney test. If you lump all those three names together, think of it as the non-parametric difference test, right? So we have a very different looking formula over here. And one of the first things I want to point out is that we've replaced our data with ranks. So imagine that you have values that look like 65, 45, and 44. Okay? In magnitude, if you think about these, 65 is really big. 45 and 44 are quite close together by contrast. So you feed those data directly in when you're computing a t statistic. But you turn that 65, 45, and 44 into a rank 1, 2, and 3 in a rank-based test. So you replace your original data with a rank instead. This makes it a much steadier kind of statistic. So once you've converted your data into ranks, you can sum together all of the ranks for one of the cohorts. So let's imagine a really simple U-test, a 3-on-3 comparison. You don't really want to use a U-test in that context, and we'll talk about why, but imagine that I have 3 data points from A and 3 data points for B. There might be a really good separation, like all of the A values are above all of the B values. Or vice versa, maybe all of the B's are on top of all of the A's. That's a best case scenario. But whether they're far apart or close together doesn't make a difference in the ultimate U statistic that pops out, and thus the p-value that comes in. So if you have 3 items, you might imagine a relatively simple intermixing of the two, right? Imagine that the top value for B is bigger than the lowest value for A. So now you've got a series that looks like A, A, B, A, A. Does everyone see that? Sorry, I screwed that up. A, A, B, A, B, B. That's better, right? Okay, so we've got this little bit of mixing. So in that case, you would have the first two A's get rank 1 and 2, the top B gets rank 3, the bottom A gets rank 4, and then the last two B's get ranks 5 and 6. Maybe I could have made a figure to make that a little clearer, but in this case, we sum together the ranks for the A's and we sum together the ranks for the B's. And here, this R1 represents that sum of ranks for one of the cohorts. The magical thing about this is that you don't actually have to sum together both sets of ranks. Because if you have 6 items, what's the total sum for all 6 ranks? It's 6 plus 5 plus 4 plus 3 plus 2 plus 1. So once you know what the sum of the ranks from one cohort would be, you can subtract from that total and find out what the sum of ranks for the other cohort would be. All right, so that number flops in here. Here we give the number of items that we have in our roster times that same number plus 1 divided by 2. And out pops our U statistic. Okay, so the T statistic and the U statistic are both just test statistics associated with their particular tests. We still need some way to relate those to a p-value. We'll talk about what that means in just a shake here. Okay, so how do we determine the probability of a more extreme test statistic? Now, I pulled some sleight of hand on you. I have broken out the concept of the null hypothesis. Is that mentioned right there? It is. So when you see H sub 0, keep in mind that is the null hypothesis. So the hypothesis we are testing, whether it's a t-test, well, we'll just start with the concept of the t-test. What we are testing is this hypothesis that the numbers from A and the numbers from B all come from one distribution. That there is no difference in the means between the values for A and the values for B. So that's the test we want to evaluate. This T statistic is the observed metric that we're trying to make this decision based upon. And what we're going to ask is essentially, how likely is it that by random chance alone, with no real difference between the means, we would see a T statistic this extreme? Okay? Now we're going to talk about sidedness in a bit, because that's a really important factor in this. But for now, I want you to just get that internalized. The null hypothesis for any t-test is that there is no difference between these two distributions. And any variation we're seeing is solely due to random chance. So, Gossett produced this publication in 1908, and it explained how these t-statistics distribute. When you have 3 samples, when you have 4 samples, when you have 50. He wanted to know this because he was trying to figure out how many batches of beer would you need to draw a broader conclusion about the processes they were trying. You know, if you had just 3 replicates of this new process and 3 replicates of the old process, was that enough to make any real conclusion about whether the new and old processes differed from each other? Wanted to know. There were no statistics at the time to tell them whether that was true or not. So this is what drove him, and because he understood how t-statistics should distribute, he was able to figure out what the probability by random chance, when no variation exists, that you would get a more extreme statistic than this. Now I'm going to show. Oh, good. Yes, this is the figure I just threw in this morning. So. I've got 2 different kinds of distributions shown here. It might not look like that, but there really are 2 different ones. So we see these dots, these little circles that are forming this bell curve shape. I think that the bell curve is a pretty familiar shape to everyone here. We call that a normal or a Gaussian distribution. So that's a normal distribution that we're looking at. Now these other lines on here are not Gaussian distributions. They look an awful lot like them, but they're not the same. And the answer is that these are T distributions. Now, we've talked a lot about T distributions about distributions having sort of a canonical shape. But in fact, there's a whole family of t-distributions. And which t-distribution you should use to translate your t-statistic to a p-value depends in large part on how many samples you've got. So if the number of degrees of freedom that you have is 2, then that red curve is the one that you would use to translate to a p-value. If you have 4 degrees of freedom, then the green curve is the one that you use. If you have 8, the blue curve. If you have 16, the purple curve. And you should notice that as the number of samples rises, the closer and closer we get to the normal distribution. So this is the principal finding here, that our ability to determine these probabilities accurately rises with the number of samples that we have to feed the t-test. Okay? Now, I'm sorry, I'm going to take a quick chug here. Okay. So, if you have a t-statistic of 2, it would help if I had a stick of some... Oh, there is one here. Perfect. Okay. Professor carries a stick. All right. Let us imagine that we have a t-statistic of -2 for a particular comparison. We want to ask, what is the probability that by random chance we have a more extreme t-statistic than this? If we didn't have any hypothesis about whether A or B should be larger, we have to remember that a more extreme t-statistic is a two-sided affair. Meaning that I not only need to ask, what is the space under this curve to the left, but also take into account the other side. We didn't know in advance that A should be bigger than B. Therefore, we have to consider t-statistics greater than 2 and those that are smaller than -2 at the same time. So this is a two-sided test. So when we do difference testing, I'm just going to set that down before I hurt myself. All right. We need to keep very close in mind whether we are doing a one-sided or a two-sided test. If you have a previous hypothesis that this treatment should make the plants grow faster, you have a sided hypothesis. If you're trying to ask, are these two plant populations different, that's a two-sided hypothesis. When you can go the one-sided route, when you have a hypothesis that being bigger is more likely, or being smaller is more likely, you can go the one-sided route, and it has a twofold difference in the p-values that come out. Because remember, the probability that by random chance that you're greater than 2 is half the probability that you're more than 2 or less than -2. It's a symmetric distribution. So our choice of sidedness has a twofold difference in the p-values that pop out. Now up at the top, we have this paired idea. Paired tests are also very, very important. So I want you to imagine that instead of comparing a bunch of plants of type A and a bunch of plants of type B, maybe you're now thinking about one plant that you've kind of kept one half in shade and the other half in light. And then you have another plant that you've kept one half in shade and one half in light. So we expected some degree of concordance between the lit half of a plant and its dark half, right? Okay, so something like that creates a paired test instead. So we'll be talking about some examples of those. Both of these concepts are pretty darn essential, though, when you're developing your statistical hypothesis testing. Okay, on we go. So I am giving some sample data here. This is a simple point, but I think people frequently miss it. So when we looked at the t-statistic, we saw that the numerator was about the difference in means, right? We saw that x bar sub 1 minus x bar sub 2. Okay, the difference in the observed means between the two cohorts. We want that value to be big, which means that if your means are further apart, it's easier to detect them. So one of the most difficult concepts in statistics, for me at least, is that of power. How many experiments do you need to do in order to detect a difference of a given magnitude? Right? So I want you to think about the further these means are apart, the fewer replicates I need to detect that. If it's a very small difference, if it's a 10% difference, you might need to throw in a larger number of samples in order to detect that difference. But you're perfectly well able, with a very small number of replicates, to detect a difference that's 100% in a twofold difference between the two. All right, now the next thing is that big variance is a big problem. T-test cares whether your data are widely distributed or narrowly distributed. In both of these plots, we have the same means in operation. We have a mean of -1 for the blues and a mean of +1 for the reds. That's true here as well. -1 is the center for the blues, +1 is the center for the reds. What I've changed here is how wide those distributions are. On the left, I'm using standard deviation 1. On the right, I'm using standard deviation 2. So from time to time, I use this term baseline resolution because I'm a mass spectrometrist. So we think to ourselves, baseline resolution would mean that these red and blue lines had fallen pretty much all the way to 0 between them. So we had a complete separation between the peaks. In reality, we don't get to deal with data that clean most of the time. So in this case, we see that when the standard deviation is 1, there's a pretty defined valley between these two. When your standard deviation is 2, however, that valley is no longer as deep. So our ability to tell blue from red diminishes. So anytime you're doing a statistical test, I want you to think, I want the differences between the means to be as different as possible, and I want the variance around that mean to be as low as possible. Good so far? Okay. So I'm going to show some R code here that explains how we ran these tests. So in this first case, I have sampled from the blue and red distributions. I have my A vector is 5 numbers, so like 5 replicates essentially, drawn from a standard deviation with a mean of -1 and a standard deviation of 1. So it's like the plot on the left. These are the samples that we're pulling in. On the right, I have a normally distributed set of values drawn from the one on the right. So 5 values and 5 values, not really cleanly separated. Now, I'm using a little bit of code called bar plot to visualize these numbers. And this is a pretty sloppy way to do it, frankly, but it's a one-liner and it's brief, so I used it. So I have given it a row binding of the 5 values of A and the 5 values of B. And I've told it that I want it to render those values side by side. So I have my A values shown in the darker bars, and my B values shown in these lighter bars up top. So remember that the B's should be centered on 1. Do they look like they're centered on 1? It's a random sample. With only 5 points, it's actually quite difficult to tell. You've got B sub 1, B sub 2, B sub 3, B sub 4, B sub 5. They were drawn from a normal distribution centered on positive 1. And the A values that we see are centered on -1. Some of them are higher, some of them are lower. It would be difficult to tell, but if I did 1,000 such samples, it would be a much clearer separation between the two. So I visualized those here. And then I ran t-test using the t.test function, A comma B. I fed it these 2 cohorts and I said, tell me whether I can reject this null hypothesis that there's no difference between the distributions. So I got back a whole bunch of information. Now, one of the first things that showed up is that I've got this name Welch involved. Welch was concerned about questions of variance. My knowledge on this is a little imperfect, but I believe in the original publication of T-statistics, there was an assumption that the variance between the A cohort and the B cohort was the same. And Welch added some variations on t-test that allowed us to use the test even when the variances were different between A and B. Okay, so the Welch 2-sample t-test has been used. The data are A and B, all very straightforward. The t-statistic here is -4.06. It computes the degrees of freedom to be 7.55. Degrees of freedom can be a little odd sometimes. So in this case we're doing a sample on those five. Those five numbers become 4 degrees of freedom, and we've got 2 such vectors of 5. So 8 is roughly the number of standard that we're using for degrees of freedom. I'm sorry, that's kind of weasel word language, but I hope that it helps to explain a little bit about where those numbers are coming from. And we see that the software does not leave us in the lurch with just a t-statistic. It translates that to a p-value for us. 0.004075. So it reminds us what is the hypothesis that you were testing under this particular examination. It was that the true difference in the means is not equal to 0. That's our alternative hypothesis. Sorry. So the null hypothesis is there's no difference in the means. The alternative says, well, there is some difference in the means. So we're able to see then that the probability that you would see a difference this big in the means by random chance alone, if there were no difference, is vanishingly small. Less than 1%. It's about 0.5%. That's the likelihood that you would see this big a difference if you had no real difference in the means. Okay, we also get some 95% confidence intervals, sample estimates, and so on. But this is the basic way in which we operate this, and you can see that it's more than just a p-value that comes back. So that is valuable to keep in mind. Now, what if we wanted to do this by a non-parametric approach? For this, we might use the Wilcoxon test, A versus B. Our friend Frank is back. So here we're going to use exactly the same kinds of inputs, sampling 5 values for A, sampling 5 values for B. We still create our plot with our bar plot function, and we do a Wilcoxon test. The feedback is a little less busy here, but again, the data that were input are A and B. We have a W statistic here, because it's a Wilcoxon test, of 2. That is mapped to a p-value of 3%. Now, the t-distribution is what you must use to translate a t-statistic to a p-value. Generally speaking, when we look at these W statistics, I believe that they can be interpreted directly against a Gaussian distribution. So we don't end up using the t-distribution with a W test in this case. Okay, so what are we actually testing here, though? People really kind of struggle with trying to put a null hypothesis on a W test or a U test in this case. So imagine a scenario like this. You have a whole bunch of, say, black and white marbles all set up in a row. So they're ranked from the highest value to the lowest value. So if you were to draw one black marble from this collection and one white marble from this collection, is it equally likely that the black would be above the white as it is that the white would be above the black? That's the hypothesis we're testing in this case. So we know that these distributions are different, and the p-value that pops out reflects that. But the null hypothesis is not that the means are different. It's to say that there's an equal probability that a randomly drawn item from set A will be above an item drawn from set B. Okay, so that's what Wilcoxon test looks like when you apply it. We get a somewhat less informative feedback from it, but that just reflects the fact that it was coded differently. Okay, now, where does Wilcoxon really show its stripes? This is kind of a puzzling example, and I want to kind of work through it with you. I have fudged the data here, right? I didn't feed it the data directly, but I produced 4 normally distributed values for the A vector, and then I added on another data point, -10. Right? -10 is a lot lower than any other value that's going to be in A or B. So A is still 5 values long, but I've fixed one of these to be this -10 value. So I've thrown in a big outlier. Now, I'm going to try different tests against this. So I'm going to try my t-test p-value first. Now, t-test is very unhappy with this situation. It has given us a p-value that is not going to reach our alpha level, our level of significance. Now, there's a big debate going on in the statistics community right now about the value of 0.05 as a threshold for statistics. But in fact, everyone in biomedicine is still using an awful lot of 0.05 cutoffs. So we're not going to get into that debate right now. But if you, as a statistician, are working over your data set and you get a p-value of 0.17, do you feel happy about it? You don't. You did not get a significant difference. Now, I've mentioned the phrase weasel words a little bit in my poor discussion of degrees of freedom. I'm going to mention some other weasel words. When people don't get a p-value of 0.05 or less, they frequently try to wiggle around the conclusion that they should draw. You frequently see that people will say very bad things like tending towards significance, or a tendency, or looks like it's different but not narrowly significant, or something awful like that. I'm going to ask us all to be honest with ourselves. Not every experiment has a significant difference. Sometimes biology doesn't have a difference for some treatment. It may be that Dave Tabb gives more energetic lectures while drinking tea than not. Or it may be that that's just my personality. Right? So sometimes biology isn't different. Sometimes the tests we put it through are not finding significant differences. So you should not allow yourself to fall into the trap that many PIs have fallen into, that my intuitions about what should cause a difference do. Reality is reality. Sometimes our tests don't have enough numbers, don't have enough samples for us to determine a difference that really is there. So it could be that your study is underpowered to find a real difference. But don't forget, nature may be pulling a little trick on you, and it may be that this thing that you think should cause a difference does not. So, use the test, interpret the numbers correctly. Don't allow yourself to talk yourself into saying things like, well, it's almost significant. Design your statistical strategy, follow it. All right, so in our first case, we see that t-test says these values are not different. Now, would you say that that's true? Are A and B from the same distribution? They are, except for the outlier. So remember, just a moment ago, I was talking about t-tests. What are the two things we need to get an observed difference in means? We need a difference between the means, a big one preferably, and we need low variance. What did our outlier do to the variance? It blew it up. It blew it up. We have a huge variance in the dark bar cohort, in the A cohort. The A cohort has a huge variance because it has this big outlier in it. And that big variance disallows t-test from claiming there's a significant difference between the two. Look at what u-test says of exactly the same data. Less than 1% probability of seeing this big a difference by random chance. So the t-test is failing here. It is not finding a difference that really is there because the variance is so high due to an outlier. But the u-test sees that all of the A values are higher than, AA is bottom, that all of the A values are lower than all of the B values. So I want you to think of this as a bunch of marbles, maybe on a Scrabble tray. You guys play Scrabble? You got the little tray that has all your tiles in it, so chuck the tiles aside, and now put marbles on there instead, right? To a u-test, if all 5 whites are to the right of all 5 of the black marbles, that's as different as they possibly can be. And it does not care where they are spaced on that marble. It's almost as though you just sort of tilted it so that they all bounced up against each other. All of the whites are below all of the blacks in that case. That is as significant as you could possibly go. This is the lowest p-value that you can get out of a 5 versus 5 comparison in a Wilcoxon test. It's the lowest p-value it can produce. And that's because there are only so many different orderings of 5 marbles versus 5 marbles. Okay, so that is our finding then with the outlier. Now, this next set is different. I've created a dependence between values of A and values of B. I have 5 uniformly distributed A values. Okay, so I had some that were short, some that were short, some that were tall, etc. And the value of B depends upon A and adds some amount from a normal distribution. Now I note that I've added the absolute value of that normal distribution. So I can only add positively to this. So I'm trying to demonstrate two concepts at the same time here. I'm trying to show paired test in that we can only evaluate the value of B taking its corresponding member in A into account. And I'm trying to show that this is a one-sided test, that the only possibility is that B has grown. So imagine you're comparing growth at 6 months to growth at 8 months. Do you expect anything to shrink? Right, so a one-sided test is appropriate in that case, not a two-sided test. So I've now run 3 different kinds of tests on these data. In this case, all of them are t-tests. I'm leaving Wilcoxon behind for the moment. So we want to compare these values of B, but only compare a B to the corresponding A. That's a paired test. So when we do that, we get out a statistic, a t-statistic that gives us a p-value of 0.032. 0.032. So we feel good about that. We say, aha, the t-test found them significantly different. We get to write up our paper, we get to publish, we get to go on to our great academic careers and become a professor and so. It's going to be wonderful. But what if we are total neophytes in the world of statistics? What if we don't know what we're doing with our spreadsheet or with R? Well, we might make a mistake. Maybe I did a paired test. I recognized that the B values could only be compared to the corresponding A, but I wasn't sure that they would always go up. I allowed for the possibility that they would go up or down. That's a two-sided test. See what happened to our p-value? It doubled. Suddenly, what looked like a significant test when we had it configured correctly no longer gives us a significant p-value. So, bear in mind at the time you design your statistical test whether this is a one-sided or a two-sided comparison. Now, what if I totally ignored the fact that I can only consider this a before and an after of the same plant? What if I thought that comparing this value to any of the high values was appropriate? If I lose this pairing between my A's and B's, suddenly my p-value is appalling, 0.13. Start over, right? Same experiment, the same data fed into all 3 versions of the same test. But we've just changed how it's parameterized very slightly. So if you have paired data, be sure you inform your t-test that they are paired. Otherwise, you're going to really just kill your test. Next, if you have one-sided tests, tell your test about it. It will probably default to two-sided, so you need to inform it specifically. This is a one-sided case. Okay. Now, what happens if I were to... I had 2 different ways, actually 3 different ways I can write my alternative hypothesis. I can say two-sided, I can say less, or I can say greater. If I set this incorrectly, if I set that to greater, then it's going to say, well, in none of these cases was A bigger than B. And it will fail as well. So you don't just need to know it's one-sided, you need to know the polarity in question as well. Okay, so that's walked through a whole bunch of stuff. The takeaways: difference testing is essential in biomedical research, but it may assuredly be misused. Lots of people don't even know whether they applied a one-sided or a two-sided test. I think that you'll know that when it comes time to do your defense, right? Especially if I show up. All right. I'll just sit back there and cry a little bit. Don't worry about me. All right, next. Students' t-test has been with us for just over a century. Did anyone stop to celebrate t-test in 2008? Did anyone stop to celebrate it with a Guinness beer, perhaps? All right. Well, so, all right, I'm just saying, this is something that we should probably have celebrated the centenary of. Keep in mind, you'll probably all be around for the centenary of the Wilcoxon test, right? 2045?
Are you using probably in the formal term?
I don't know what you'd use to celebrate a Wilcoxon century, though. I mean, would you fire off ordnance? I don't know. We'll see if anyone's around to do it by then, right? Okay, so be sure you know whether your data are paired and if a sided test is appropriate, because that will make a big difference in the magnitude of p-values that pop out. When your data are